Hi everyone. I hope you're keeping well and that you enjoyed the half term. Regardless of whether you chose to get studying or to kind of recharge the batteries a bit, both options are good as long as you're coming into the final stretch kind of recharged and ready to go. So I've spent a decent chunk of the half term going through the mocks and I've come up with answers for all the questions involved. I've written them all out ahead of time just to speed things up on these videos. Now, at the outset, I've got two kind of quick caveats I wanted to say. The first is that I'm not going to let perfect be the enemy of good on this. So I might make a mistake here and there, or stammer, or hesitate or something on this video. But this is like take 6 of trying to do this. So as it stands, I'm just going to let it roll. So that's the first thing. The second thing is I left the mark scheme for the mocks in school, so I don't have access to that. Now that's not that much of an issue for the section A, for the experimental section, because I've done it so long and they're so kind of predictable in a lot of ways that I can tell pretty much how the marks break down. For the higher level theory section in particular, and for the theory section at ordinary level, that's a little bit less predictable, but I have a pretty solid shout on the kind of things they ask. But that being said, when we go back, I'll have a gander, and if there's any kind of amendments or anything to make, I'll let you know. On the same breath, it's quite possible I've made a mistake here and there. If that happens, I'll draw your attention to it. But for now, let's get cracking. So, first section we're going to look at is the experimental section. We're going to look at ordinary level, then higher level. For the sake of speed, it would help a lot if you've got your own copy of the mock, which I asked you to keep hold of in front of you. Just because I'm only using this to keep myself on track, really. I'm not going to be referring to it. It's mostly going to be the action on these answered questions here. Second thing, and I don't know if I've already mentioned this, but I want you to think of the experimental section, section A. Make it your friend. Don't look at it as an obstacle to overcome. This is a place where you can lock in 120 out of the 400 marks, and it's quite possible to achieve a decent chunk of them, both at ordinary and higher level. And that means that you're getting close to crossing the line on that alone. Now, it's not enough, but having a really strong performance at section A will really help you get to a good grade, regardless of where you're coming from. And the good news is they're very predictable. Like, they're not predictable in the sense of which topic will come up. That's kind of anybody's guess. But in terms of what they ask for each experiment, it's very cyclical and predictable. Another note just before we really get cracking is that white experiment book is invaluable for studying for this section. Obviously, just to go over the experiments themselves. But at the start of the book, there's a whole section on how to process the data and do the graphs. Now, I don't have mine to hand. Mine's not in my house at the moment. But it's kind of a summary of how to do the data processing for basically all the experiments. So I know that a lot of you, when it comes time to do these kind of questions, you'll remember the experiment, you'll remember us doing them. But how to do the graph or to manipulate the data or run the equation or whatever, that might be a bit rusty. So that's what I'm saying. This first section of that white book is really, really useful for that. So, that all being said, and like I said, if I make a mistake, I'm going to keep on trucking rather than reshoot this because I've lost track of how many takes this is. But that being said, let's kind of get moving. So we're going to look at the ordinary level experimental section first. I'll put a timestamp on the video after the fact, so if you're doing higher level, you can skip on to that section. So I'm probably going to do the experimental section and a separate video or videos for the theory sections. Okay, so let's get cracking. Section A, first question is a moments and turning forces one. They want you to sketch out the apparatus used for the experiment. So that's a meter stick, two Newton meters bringing upward forces attached to a torque stands. And then in this experiment, we've got 2 sets of known weights attached, and you've also got the weight of the meter stick itself. Sometimes the higher level one, they might have 3 or 4 weights attached, but regardless, the science behind it is exactly the same. So first question, draw a label diagram, done, showing all the forces acting on the meter stick. So we got forces down, forces down, force down, force up. Really, should probably label these F. Just to be absolutely clear. Don't leave them in any, doubt when you're trying to lock in those points. Okay, so second part, which force is most likely to be the weight of the meter stick itself? Well, it's the one that's at the 50 mark, halfway along the meter stick. That's most likely to be the weight of the meter stick itself because it acts in the center of gravity. It's also, if you look at the magnitude of the forces involved, it's much more likely to be 1.6 newtons than, something that's like 16 newtons, which is a lot. So, yeah, it's the one in the center, the one at the 50 centimeter mark. How are the upward forces applied to the meter stick? They are applied via the tension in the Newton meters. Calculate the total upward forces and total downward forces. Well, the upward forces are the 2 readings on the Newton meters, 8 newtons, and 15.6, giving us a total of 23.6 newtons. And the downward forces are the sum of the others, 6, 1.6, and 16, giving 23.6 newtons down. So there's no net force acting on it. Question 5, explain how these values verify one of the laws of equilibrium. That's just kind of what we're alluding to there. Because the total forces up is equal to the total forces down, there's no net force acting on the meter stick, so it experiences no acceleration, which I think I probably misspelled there, but it is what it is. So it's not going to accelerate up and it's not going to accelerate down. And in this case, because it was static, it's in a static equilibrium, it ain't moving. Okay, part 6, calculate the sum of the anti-clockwise moments of the forces upwards around the 0 centimeter mark. When I say about the 0 centimeter mark, imagine that's your fulcrum. They just mean, imagine that's your rotor. They just mean that we take the fulcrum at the 0 mark, so at the start, and then balance it like that. Whether it's going to go up, which forces are going to cause it to go up, and which forces are going to cause down, or clockwise, anti-clockwise. So, calculate the sum of the anti-clockwise moments. Okay, so let's do that first. The ones that want to make the rotor go anti-clockwise. So if we're going from the 0 mark, I'll just zoom in a little bit here. Okay, a little bit. This probably isn't going to be a short video, as you probably figured out by now. Anyway, so anti-clockwise moment, we have these two guys here. They're going to cause it to move anti-clockwise. So the 8 newtons, which is at the 0.08 meter mark. Be careful of your units here. They give it to you in centimeters. You've got to convert it to meters. That's a bit of a nasty trap. You expect it more at higher level, but there it is. So force times distance from the fulcrum, force times distance from the fulcrum. The total anti-clockwise moment is 13.9 newton meters. And for the clockwise, it's 6 times 0.35. So these are the other 3 forces acting. The 6, the 16, and the 1.6 in their respective positions, adding up to a total of 14.9. So it's pretty much equal. It's a little bit off, which is a bit confusing, and it's a bit annoying they've done that in the ordinary paper, but it is what it is. So we have our total anti-clockwise moment is 13.9 newtons versus 14.9, which is roughly equivalent. So the anti-clockwise moment is equal to the clockwise moment. There's no net turning force. There's our answer to part 8. Okay, that's the first question. Let's have a look at the second. I'll just zoom out there a little bit. I might just get that light off. I think it's probably making things worse. Okay. Question 2. This is the acceleration due to gravity question. So this is the free fall one that we had to kind of MacGyver a little bit, but let's have a look. So let's look at the question first. They give us our table, and they give us already, they point out to us that we're going to need the t squared rather than the time. So what are we doing here? We're dropping a ball bearing from an electromagnet onto a trapdoor, which is, both of them are connected to a timer. So when you press the switch, 2 things happen at once. The electromagnet loses its power, causing the ball bearing to start to fall, and the timer starts. And then when the ball bearing impacts on the trapdoor, it stops the timer. So you get a very precise reading of how long it took to traverse that distance. So there's our label diagram. Make sure you've kind of labeled everything. Again, patronize the examiner. Make sure you've left no stone unturned. So the meter stick labeled, ball bearing, electromagnet, timer, trapdoor apparatus. There's your points. Okay, indicate in your diagram the distance that was measured. You got to be very precise here. It's measured from the bottom of the ball bearing to the top of the trapdoor. So the actual distance it's going to fall. And I've just written it out again. Don't leave anything to chance. Write it out. Be explicit. Take your time and write the sentence, even though you've got it on the diagram, have it there as well. Okay, copy the table above into your answer book and complete it. All right, done and dusted. So all you got to do is square the time values. For a quick kind of reasoning as to why, okay, let's just kind of go over why that is the case. So going from the standard motion equations, S equals ut plus half at squared. So that's the displacement, initial velocity, time, acceleration, time squared. So because it's dropping from rest, the u part is going to be 0. It's got no initial velocity. So that simplifies down. That first bit just goes away. So we have the displacement is half at squared. So we can rearrange that to be, if you just bring the t squared across, you have s over t squared is half of a. So if we were to graph s versus t squared, and if you think about what slope is rise over run. So how far has it gone up versus how far has it gone across. So we get the slope of this. That slope is going to be half of the acceleration due to gravity. Okay, let's get on to the grapher. Nice, straightforward, linear fella here. or for at least for this part of it. Oh, it's not very dark. So let's just keep track of where we are here. Easy data to draw your graph. Okay, so essential things. You got to have your labels on. S is displacement measured in meters. T squared measured in seconds squared. Plot your graph. Make sure you've got enough room. Make your life as easy as possible. You're always going to have 9 boxes going across, 14 boxes going up. You can do it landscape, you can do a portrait, just as long as you can fit it and as long as you can get your units on, you're good. Okay, so there's our graph. The acceleration due to gravity is twice the slope, that's what we just mentioned there. So measure the slope of your graph. Okay, so choose 2 points in your graph. I'm going to zoom in a little bit here. Choose 2 points in your graph and do the slope in between them. For the sake of ease, I went with the 0.05 and the 0.15 for the horizontal, just to make it a little bit more straightforward. So switching over here, here's my slope calculations. My first point, 0.05, 0.25, let's go there. And the second one is 0.15 and 0.74. So there's my 2 points. The slope, but I'm going a little faster, so I'm going to slow down a little. So there's my 2 points for the graph. You can choose any 2 points on your line of best fit, but the further apart they are, and if they're in a nice interval, it makes it a bit more straightforward. So to rise over run, 0.74 minus 0.25 for the rise, 0.15 minus 0.05 for the run. Works as being 4.9, nice and, suspiciously exact there, isn't it? Because that's half of the 9.8 that we know and love as being acceleration due to gravity. So if g is twice the slope, that's twice that 4.9 to give us a acceleration due to gravity, of 9.8 meters per second squared. There's our second question. I'll keep cracking on. We've got a bit of pace going out. Let me just zoom out here a little bit. Okay, so question 3 is a Snell's Law. Great name. Snell's Law experiment. Student carried out an investigation, blah, blah, blah. Draw a label diagram. So Snell's Law is when we're trying to measure the refractive index of material, or we're trying to prove that the refractive index of material, is the relationship between sin I and sin norm. So what's the setup? Okay, it's the one where you've got a ray box. You shine a ray of light at a glass block and see how it refracts. While it does refract through here, again, at the other side, we're not really too concerned with that. We're concerned with this initial refraction here. So make sure you've labelled everything. Your ray box, incident ray, the normal, essential that you draw that in. Refracted ray inside, and it's bending towards the normal because it's going into a denser medium. Angle of refraction, angle of incidence, I think that's one of the later questions. And again, patronize them. Draw a protractor, just so that they know that you know how to measure an angle. So that they know that you know that they want to know that you know how to measure an angle. I'm going to stop now before this gets to the city. So your protractor and the search pins. Now we didn't actually use these, we just used dots on the paper. But again, just be explicit, flash them in. Okay, so draw a label diagram, done. Indicate in your diagram the distance, I'm looking at the wrong question. Draw a label diagram, done. Indicate in your diagram the angle of incidence and angle of refraction. There's your angle of incidence between the incident ray and the normal, and there's your angle of refraction. The angle is between the normal and the refracted ray. Explain how the position of the refracted ray was determined. So I've been really pedantic here, guys. Like I really kind of spelled everything out for them. So use pencil marks or search pins used to mark the points along the incident ray and refracted ray. Draw around the block. Ruler used to join up the incident ray and refracted ray. It's just specifying using a ruler the whole time. So like you draw around this block. Let's go in here. Draw around the block, draw the incident ray, draw where it refracts outwards, join those two up with a ruler, draw your normal and measure the angle of incidence with the protractor, angle of refraction with the protractor, and then we're going to graph sin I over sin R, which is our next bit. So that's like being as pedantic and detailed as possible. I'll bring all these sheets in, guys, so you can have access to them if you can't quite make out what I'm doing, if I'm going too fast or whatever, so you'll have access to them when we get back. Okay, copy the table into your answer book and complete it. So there we go. There's our I and R with our sin I and sin R. And they're trying to be nice here because the number one mistake people make in these kind of questions is they graph incidence versus refraction. And it's not the angle you're graphing, it's the sign of the angle you're graphing, because that's what Snell's Law is all about. That the refractive index is the ratio of sin I over sin R. Copy and complete the table, done. Use the data to verify Snell's Law. Okay, now, I'm wondering if there's a smarter way of doing this than I did. I graphed it. I wonder if you could just do an average. No, you can't. Okay, so you have to graph sin I over sin R. because Snell's law is that N is sine I over sine R, which I've just written above if I read. So we need to graph it, sine I over sine R. And again, just like before, choose 2 points on your graph, use them for your slope. So I got a slope this time of 1.55, and that slope is the refractive index of this material. And they don't really want us to actually get that exactly. They just want us to establish that it's a constant term. That for this material, sine I over sine R is a constant. They're giving you that nice straight line graph. Okay, I'm going to keep cracking on. I know I've probably meandered a little bit from where I meant to go. Okay, I wouldn't have chosen this next one, guys, and in fact, I doubt any of you did. It's on a topic that we've done, but an experiment that we haven't / can't, because it's a bit, we don't have the steam trap or the heat stuff to do it, and it's a bit of a wobbly one. We've done the fusion due to ice, which comes up a lot more often, especially in ordinary level than this fella, but it does come up from time to time. So this is again about latent heat of fusion, latent heat, this time of vaporization, not fusion. So like I was saying, I wouldn't have chosen this one. This is a bonus one. You know, I'd have done 1, 2, 3, or 1, 2, and 5. I think we're already in a position where we're 3 out of 5, but just for the sake of completion, we'll do the last 2. Okay, so draw a label diagram. You heat up this water, you boil it, it turns to steam, it goes along this pipe. The steam trap, the idea is that it's only pure steam going in, not any condensed steam. That's the idea of that. Delivery tube brings it right into the water itself. And then you measure the increase in temperature of the water. And obviously before you do all this, you establish the mass of water that you've got. I'll breeze through this one quite quickly, guys, to get to ones that we've done and that you're a bit more comfortable with. State 2 measurements that were taken before adding the steam to the water. Well, how the mass of the empty calorimeter, then you add the water, so you measure that mass as well, and then the temperature of the water. So there's 3 things of the 2 they're looking for. Excuse me. How is the state 2 measurements that were taken after adding steam to the water? Well, the temperature, the highest temperature it reached in the calorimeter, and the final mass of everything. So when that steam is condensed inside, the mass of the calorimeter, water, and condensed steam. This is very similar to the fusion of ice one we did, where you measure the mass at the end to include the melted ice. Okay, part 4. Explain how 2 of these measurements were used to find the mass of the steam. So you just subtract the final amount, which has everything, from the mass that you had before you added the steam. And the difference is the mass of the steam. Why was the steam trap used? To ensure that only steam was added and not any water. Okay, final order level question. Before we switch gears onto the higher, I might do the higher one in a separate video in a second, actually, because this is probably getting quite a bit long. I can't tell at the moment. So let's do the last question, at least, anyway. So the ordinary level, question 5, last part of the experiment question. In experiment investigation, the resistance between current and potential difference across a semiconductor. Okay, so I've drawn in the one that we used for this when we're doing about the metallic conductor and stuff, rather than in your experiment diagram, there's one showing a potential divider, like the variable resistor, whereas we have variable power packs and we're able to alter, I don't know when I'm doing this gesture, you know how to turn the dial, we can alter the voltage of the power units. So there's our setup. We have the variable power unit, which we can alter, the milliammeter, measuring the current going in, the semiconductor itself in forward bias, where you have the line bit connected to the negative bit, that's the negative bit. I hope I haven't got that backwards. There's a distinct possibility, but I'll double check after. But that's forward bias, and you have the voltmeter going across it, measuring the difference in energy potential, electric potential energy going in versus coming out. Okay, how is the potential difference varied in this experiment? Well, if you use the variable resistor, use the variable resistor, but we didn't. We just used the variable power unit and altered the voltage. How was use the data to draw the graph? Okay, this is a bit of an odd looking graph if you look at it. So you got a kind of a linear increase up to there, and then it goes bananas. It goes crazy. That's that exponential rise you get when you cross the threshold voltage. So there's the graph. Again, it's an odd one. No straight line of best fit is going to do the job there. That's your curve. And again, make sure, I should be overemphasizing this, because make sure you've labeled everything, So there's current on the y-axis, voltage, units is volts, units is milliamps. Does the semiconductor obey Ohm's law? Well, if you remember, Ohm's law states that the voltage-current relationship is going to be a constant, a nice straightforward straight line. This is not the case. So Semiconductor does not obey Ohm's law, as the relationship between voltage and current here is not linear, it's exponential. Because I know I said I was going to do this in one video, but I think I'm going to break this up mainly because I've covered my higher level questions with other stuff. And I think this video might crash if I try and go too far with it. So I'm going to just stop here and maybe do the higher level as a separate thing.